So I think we can start now. It's the right time. So good afternoon, everyone. You cannot see here, but we are in a big auditorium. Unfortunately, very few people attending right now, but let's hope that someone will be online and also in presence here. So we have this big workshop today in the afternoon, which is about the renewable heating and cooling solution for buildings and industry. We'll have 20 projects presenting their activities and also a short slot for the European Heat Pump Association that will present us their activity on creating a database about the renewable heating and cooling projects. So I will go very fast. Okay, here we have the first slide. Okay, as I already anticipated, we will have 5 different technical sessions during the workshop. I will give a very brief introduction and then I will leave the word to Dan for the presentation of EHPA about the Renewable Heating and Cooling Project database. And then we will go for different sessions starting from industrial applications, then we'll move to storage technologies, low TRL renewable heating and cooling solutions, high TRL renewable heating and cooling solution, and then we'll end with the renewable heating and cooling solution for NZEB application. At the end of each session, we'll have hopefully 10 minutes. That's the time allocated. So if you will be able to keep your 5 minutes slot to complete your presentation, we'll have enough time to, question and answer, and also to share some experience gained during our activities in the projects. So, extremely brief introduction from my side, so we can save time for your presentations. As you know, this is the second time we go for this workshop at Sustainable Places. We organized the first one last year. It was fully virtual workshop. Also, last year we had, I think, the most populated workshop with 16 projects. And also last year we decided to cluster them in different sessions just to try to make the presentation. It's also the discussion focused on the different topics that are related to the renewable heating and cooling solutions. This year, the main innovation is that we will have a new topic that was not present last year, which is the one about renewable heating and cooling solution in net zero energy buildings technologies. So we'll have 5 projects presenting their activities, especially the ones focused on renewable heating and cooling. What we try to do this year is to focus the presentations and then the discussion mainly on the relevant innovations that each project are proposing, and also the challenges and barriers that are faced, especially in this strange period. So this was the introduction from my side. I will now leave the word to Dan from EHPA that will present their activity on preparing this database about renewable heating and cooling projects. So Dan, the floor is yours. I will move the slides for you.
Thank you so much, and good afternoon, everyone. Hope you can hear me, see me, as is the usual greeting nowadays. So my name is Dan Stefanica. I'm the head of EU projects here at the European Heat Pump Association, and it's my pleasure to present to you a project and an opportunity that we have been engaged for a long time. This is, of course, the European Technology and Innovation Platform on Renewable Heating and Cooling, and specifically, and by the way, you can see there the web page and all the necessary links. Specifically, it's my pleasure to introduce you to the project's database on renewable heating and cooling. The next slide, please. We've been working on this database for quite some time, actually since the beginning of the project, so a few years now. This database, it's actually a one-stop shop that gathers all of the projects that we find to be relevant for our sector of renewable heating and cooling. So be it projects that use heat pumps, biomass, solar thermal, and so on, they are very easily findable. There's a lot of information that is there. We use filters, so you can filter for the application area, for the technology, for the TRL. And it's a very easy way to keep track of all these projects. So whenever you want to find information, you want to find contacts, you want to find projects to build upon or projects to collaborate with on the project that you're working on or the project application that you're thinking about, then this database is really easy to use and to submit your project towards it. As you can see towards your right, and hopefully all the screens are the same and it's not mirrored in any way, one of the projects shown here, it's actually going to present later. So as you can see, there's the logo, the description, all the links possible so you can find other information. And you can also see the filters that allow you to find the projects that you're looking for. There are buttons all over the RHC website that say submit your project or join the community of projects. That is the way to do it. And believe me, it will not take you more than probably 10 minutes to submit your project. Then we will approve it. We will let you know if anything is missing. And then, of course, your project will appear. So very, very easy. And the next slide, please, because the presentation will be very, very fast. It's also, like I said, we've been working a lot on this, and we want to not only continue with it, but also expand upon it. So we have been always updating the projects with the ones that are self-submitted, as well as with the ones that are newly funded by any funding agency or EU fund that we are aware of. We want to encourage the collaboration of projects. So now it's just a database, but in the future, we want to expand it to a collaboration database, so where you can find partners much easier. We want to combine this database with matchmaking events that we've started to already develop under the RHC project. And we want to basically create new projects that build upon the database and the database resources that exist. So more projects, a more expensive database, and more opportunities for you, either in matchmaking, building upon what you have now, or building the next generation of renewable heating and cooling projects. That is all for me. Please submit your project, and please let's expand this database. Thank you so much.
Thank you, Dan. I hope you can stay with us for a while, at least to attend to the workshop. So if you have any doubts, question for the speakers, of course, you are welcome. So we now move to the first session of the workshop, which is about the industrial application for renewable heating and cooling. Here it is how we organized the presentation on the template that we asked the colleagues to follow. So we'll have a short introduction of each project, the relevant results achieved so far, and the barriers and challenges faced. So the first session will have 4 different projects. In principle, 3 of them are supposed to be remote, so I will ship to Fair and Friendship, while a step should be presented by Joan Enriquez, which should be present here. I don't see him, but no? Okay, we'll see. The first 2 projects are, let's say, 2 innovation actions, so ITRL activities, while the other 2 are RIAs. So we'll also see different approaches and different levels of development. So I would like to welcome Dr. Uli Jacob, that will represent the IBUILD projects and is the first speaker today. Please, Uli, the floor is yours.
All right, thanks, Andrea. Thanks for the introduction. It's my pleasure to be here in the Sustainable Places conference, the second time, to present renewable heating, cooling applications and information about the research projects. In this case, the HyCool project, which is looking into the use of solar heat for industrial purposes, especially for cooling, heating, and to provide, in that case, 2 vectors of energy to dedicated applications in industry, especially in the food sector and the chemical sector here in this project. My name is Uli Jacob. I'm the managing director of GER, a consultancy, which is, of course, one of the project partners. Next slide, Andrea. Yeah, just to introduce to you the project itself. Of course, we also try to bring a solution on the market in that innovation project, how to decarbonize the industry using solar heat, in our case, to use Fresnel collectors, which are supplying steam or hot water, however, and to use that again through adsorption chillers to convert it also into cooling. So it's not only heating and steam application, but it's also cooling for industry. And with that, we have three kinds of energy vectors which can be supplied with a high efficiency to industry applications. And the innovation, especially in that project, is that we use a hybrid chiller, which is not only using the heat from the Fresnel collectors, but it's also a combination with a conventional compressor chiller. And with that, we have the chance also to provide temperature levels below 0 degrees, especially for ambience, where we have high ambient temperatures, or especially for southern European regions, for example, where we have these two pilots in Spain. The major goal of the project is, of course, to demonstrate this kind of solutions, these innovative technologies. It's an innovation action with 15 partners from 10 European countries. Next slide. Now, what are our relevant results so far? In 2019, we developed a pre-feasibility simulator tool, which allows you, which is an online platform-based system, which allows you to investigate whether the high-cool technology is suitable for you, for your industrial purposes, and makes it easy to get already an answer if that somehow fits with your needs. In 2020, we did a lot of lab testing, especially CNR, so Andrea and his team, to evaluate this hybrid chiller for different cooling purposes, so for process cooling and also refrigeration. And there they already achieved high numbers on EERs between 1.5 to 4.2, which is quite nice, especially with conventional compressor chillers. And you have to note this solution is using only natural refrigerants. And with that, it's also some specialty, which is somehow an innovation in this project. This year, we have the main focus on the pilot side, which means the installation of Fresnel collector fields. One of them you can see at the top of the slide. And also, of course, the installation of the hybrid systems with the chillers and so on. Next slide, please. Now, what are the main barriers and challenges in this project? Of course, first of all, in such projects, you have to think about where and how you can integrate renewables. You have to find the entry point, and therefore, the assessment of the existing industrial processes is essential. So with that, it's sometimes a barrier, but also it gives you the chance to think about new solutions. Another barrier probably is also the construction side itself. Depending on the building type, the roofs and so on, you are often limited, especially for industry applications. And there you have to look for different issues, which also somehow difficult. On the other hand, what is now a challenge for us, especially with the COVID-19 situation, are delays within the system installation of this pilot site, where we have started in October last year at Dividend plant, in April this year at Bode de Bo, near Barcelona. And all those things, not only restrictions from COVID-19, but other delays, caused some delays in the overall installation time, which then leads at the end that our monitoring phase was part of that project will be somehow shortened. And with that, it's also somehow a challenge now for us, especially for the partners from university institutes, to evaluate the systems in a very short period. If you are interested to get more information about the project, then you're warmly welcome to visit our website. You can find more information about the project itself, a lot of deliverables, and of course some other features like videos and so on. And if you have more questions which we can discuss during the discussion session, you're also welcome to send us an email. So thanks for your attention. And,
Thank you.
welcome.
Thank you, Uli, for keeping the time. We now move to the next project, which is presented by Guglielmo Cioni from TVP Solar, which is Ship to Fair.
Hello.
Guglielmo.
Good afternoon, everyone, and thanks for inviting me to present you the Ship to Fair project. I am Guglielmo Cioni. I am the Chief of Business Development in TVP Solar. We are one of the technology partners of Ship to Fair. We are manufacturers of the high vacuum flat collectors that are being employed in some of the demonstration activities of Ship to Fair. Ship to Fair stands for, is about the application of solar heat in industrial process with specific reference to the agro-food industry. And why agro-food? Because agro-food, of course, is a strategic sector, and its energy independence and resilience, I believe, are quite important for the overall stability of our system. You can move on the next slide. Thank you, Andrea. So, as I was saying, decarbonizing industrial agro-food production. The agro-food industries are quite energy consuming, and in particular, they use a lot of heat at low and mid temperature, both in the form of hot water, sometimes in the form of steam. Therefore, we decided to put together quite the consortium. There are 15 partners, and 4 of them are technology producers. We are one of them, but then, of course, there are others like Industrial Solar that is implementing demonstrations with the Fresnel systems, and also we have Solid, which has implemented an interesting demo in the field of winemaking. Of course, this is not only about demonstration. Before that, there is the development of 2 interesting tools. One is a replication tool, and the other one is a control tool. Replication tool is about suitability of any industry to accept solar heat. So because of their position, geographical position, and because of the kind of the level of heat that they use, any industry may be more or less suitable to accept solar heat, and any solar project can be more or less interesting also from an economic standpoint. So the replication tool aims at determining as quickly as possible a first assessment of the visibility of a project. The control tool instead is about, the development of the control tool is about determining, optimizing the integration of solar heat into these processes. So applying sophisticated techniques of forecasting, weather forecasting, and load forecasting in order to maximize the applicability of solar heat in this process. You can move to the next slide if you like. So results, the control tool and the replication tool, as I told you, has been already developed, and they are available now in 2019 and 2020. Then, of course, COVID came and we had some delays, but still we have managed to install the first solar system, in particular the one based on the winery in Spain. And this is dedicated both to the production of heat, but also of cooling, for the control of temperature inside the wine holding rooms where they make malolactic fermentation. In the 2021, we have commissioned a second solar system based on our technology, TVP Solar, that is dedicated to production of steam in the Martini and Rossi factory in Turin. This is quite a feature because Turin is not such a big irradiation, but anyway, we managed to use steam at 4 bar. The third solar system will be installed shortly, and in fact, I am coming from this site, and I wanted to be with you today in person, but I had to go to visit this meat manufacturing. This is a duck meat manufacturing company in France, and I will come back on this later because of the challenges that we have to discuss. The fourth will be implemented in 2022 as in a sugar making factory. And then there will be, of course, a phase dedicated to the monitoring of how the system works and how effective it is to reduce the consumption and the carbon emissions of these companies. Let's move to the next one, Andrea, please. So First of all, I won't go into detail of barriers and challenges, but I really want to speak about one particular challenge, that is the integration into the thermal processes. I mean, we assume sometimes, and we did so in this project, that all our target industries, in particular agro-food industries, are fully equipped to accept signals and to provide data and to operate automatically a lot of controls to optimize their energy consumption. So let's be very clear, it is not like that. So of course, for example, some of them, they are. Martini & Rossi is a fully digitalized industry, while, for example, 2 days ago, I was in France, and for example, in this company, L'Arnaudit is an important partner, where we will make, let's be clear, these demos are not like small demos. This is a megawatt scale demo. And they have no instruments that can easily collect the data and send it somewhere else, etc. And the culture of the agro-food industry is sometimes a bit traditional in their nature. So it's difficult and it's hard to find good integration point to get data about where to integrate, when they need energy, how much energy they need. All of this is really in the head of the plant manager, and this needs to be extracted and in some way make it systematic. So I guess that user acceptance is becoming more and more, less and less a problem, because with gas and fuel prices going up, everybody is ready to accept free energy from the sun. So for the rest, I would say regulatory requirements, yes, it's a barrier. Let me tell you that even with a European project like this, with the evident meaning to get the approval for constructions from even on his own rooftop, sometimes it takes time. In the case of this French factory, we have to install on the ground, and it's 1 year that we are battling, and finally we get it. So I guess in terms of cost, I won't discuss. Of course, the gas has been very cheap, but it's not like that anymore. So I suppose that this, together with the incoming carbon prices and growing carbon prices, is something that can be addressed with these demonstrations. Of course, I would love to for you to be interested in knowing more about Ship2Fair. You can go on the website, but don't go on the website. Please get in touch directly, either with me or with other partners or with the coordinators, Circe. Thank you very much.
Thank you, Guglielmo. Okay, so please, Valerie from Friendship, Valerie Guillermo.
Yes, sorry, can you hear me?
Yes.
Okay.
So he's the coordinator of Friendship Project, and please, the floor is yours.
Thank you. So good afternoon. Yes, so today I will briefly talk about the status of the Friendship Project. This project has been founded by the European Commission in the framework of a call dedicated to solar heat for industrial process, specifically in the mid-temp range. The project started in May 2020, and so tomorrow will be the starting of the 18 months 18. Okay, next slide, please. So as shown by Ship2Fair and Guglielmo in the last presentation, solar heat can already be used for industrial processes in the low temp range. And there are a lot of recent examples in France, for example, showing that there is market for solar heat for food and agro industries. And the goal of the Friendship Project is to demonstrate that this solar heat can also be reliable and cost-effective for industrial processes in the mid-temp range, so up to 400, 500 degrees Celsius. The approach of the project is to develop more cost-effective and reliable cheap solutions, and also to increase the awareness through active communication. Regarding the team, so the team is composed by RTOs, concentrated solar techno providers like Absolicon and Industrial Solars, also end users and engineering and consulting companies. So as you can see on the picture on the right, the project is built on 4 pillars: increase the temperature supplied to the process, open application to cooling, support solar stability, and also provide a better integrability into the process for the solution. Next slide, please. So about the results after 18 months. So first I have to say that in Friendship Project, we're working on a system and its control and operation. And the system, as you can see on the top right, consists of following main components: a solar field able to provide the heat at mid-temp range, a high temperature heat pump, an innovative combined heat storage capable to store heat from the solar field, but also from the excess heat from the industrial process, and the multi-stage absorption chiller to deliver cold. Work package 1 was dedicated to the system specifications and requirements for the system. It is now completed. And those system specification and requirements have been defined according to the needs from our end users in the project, but also from broader perspective for industrial sectors like textile, plastic, wood, metal, and chemistry. So after completing this work package 1, all the VPs are dedicated to the development of components are now started. And the status is as follow. So the end user's case, specific PNIDs and initial solar balance of plants are now available. Concept for steam heat pump and reverse Brayton CO2 heat pump are established. There is 2 architectures in balance for the GAC absorption chiller that is in consultation phase, and there is 3 design in balance for the combined storage, and they are in consultation phase also. All those components will be tested individually in 2022 and then as a system afterwards. So finally, regarding dissemination, we are doing well so far. There is 2 papers published, 3 papers on submitted, a blog article on SINTEF website, and several participation to conferences and workshops. So if you want to know more, please let's go to our website, and there is more information and links. Next slide, please. A brief talk about the barrier and challenge. So for the ship at mid-temp temperature, mid-temp range, sorry. So from an engineering perspective, there is a lack of information about detailed heat loads and temperature levels from the industry and other data also. And on the other hand, there is a lack of knowledge of the industry about available and reliable solar thermal technology. If we go to the challenges, I think industry must forget the old habits like using oil or gas boiler because it's a proven technology, and let's say just switch to biogas, for example. And challenge number 2 is rising. It's that policy must move away from the whole electric concept, which is not a real sustainable option. Thank you.
Thank you very much, Valerie, for your introduction. So we go for the last project, which is AZTEC. I saw Joan is actually online, so
yes.
not
Hello.
present here, unfortunately. So you have now 5 minutes to present the project. Thank you.
Okay, thank you very much, and good afternoon. I'm Juan Enriquez. I'm the CEO of Analysis DSC. We are one of the partners of the AZTEC project. The AZTEC project is the sister project of Friendship, and we are it's application of solar thermal energy to industrial processes. Okay. The idea is to create an innovative solar and heat industrial processes, and it's based on 2 very innovative designs. One is the rotary Fresnel collector that is developed by UPM and UNED, and actually UNED is the coordinator of the proposal. And additionally to this, we have a thermal energy storage that is developed by PWR, is the Technical University of Wrocław, University Polytechnic of Cartagena in Spain, and AZTEC, our company. And then over this, there's an integration of control system to apply these two innovative technologies for the two use cases. As you can see, this is the approach. Basically, we follow the standard distribution of working packets and tasks. Initially the requirements, and then the development of the sundial and the thermal energy storage, and the integration of all of these aspects, then the construction, the deployment, and then the communication, simulation, exploitation. As it's a similar scope than the friendship, the idea is to answer the need from the industries in the midterm temperature range up to 200-400. For that, as you could see, the team, the project that started last May 2020 is formed by 15 partners in 8 countries. We have the representation of academia, RTOs, SMEs, and then industrial partners. Especially in the industrial partners, the 2 use cases were dairy production plant in Greece, and especially that very innovative solution of the solar collector that is able to move in 2 axes. We are able to answer the needs of end user that will be northern than the usual regions close to the Mediterranean in the European context. Okay. With respect to the deadlines and the time scale of the project, as we're starting to 2020, during this year, and the idea is that in order to have one entire year of testing, and from the last of 2023 to 24, we'll moving ahead the development of the main innovative concepts, the sundial and the thermal energy storage, to the end of this year. Especially because it's very critical, because we need to prove how this concept is working for such a north country as well. The second use case is located in Iasi. It's in the northern part of Romania, and which is very difficult because depending of the month of the year, there's not so much solar radiation. Okay, during the next year in 2020, we'll start the actual construction of the 2 pilot plants. Initially, it will be tested in the university in Madrid and in Cartagena, in Madrid, in Spain as well. And then after this construction will be the deployment at the end users locations, and will be testing it for 1 entire year. Okay, so we're next, please. Okay, with respect to the barriers, basically one of the advantages of the innovative solution is the compactness of the solar collector, and also that's one of the advantages that our system is. We have the barrier of the lack of compactness of the thermal storage, because at the end is very big thermal storage in order to cope with the different needs of both the steel industry. That's for the Iasi case is for ArcelorMittal. That's for heating needs, and also the same thermal needs for both cooling and heating for the dairy use case in Mandrekas, located in close to Corinto in Greece. The second, okay, as you can see, the barriers is usually the same time the money, the cost. So one of the advantages of our innovation related to the solar collector is that that is easier to build locally. So we'll have a differentiation with respect to other competitors in this case. And then the challenge, and we try to prove using a high north location like the one in Yassi, is that the Fresnel collector, this one, the sundial, that is under patent from UNED and UPM, that is able to move into different axes. And then actually the other challenges that they're usually the ones related to solar thermal applications. Okay, and I think, yeah, okay. So, and then you can follow us with respect to the dissemination and communication. Besides this application, we have already submitted some publications and presentations and solar passes. Right now, 4 of them, and 1 in NSTOC as well. So we are doing quite well, especially also in the social media. So you can reach our information in the web page and also through the LinkedIn and Twitter. So
thank you, Joan, for your presentation. So we are a bit short in time. I would say 5 minutes for question and answer. I have a first question for mainly for Uli and Guglielmo, because they both mentioned that one of the main barrier or challenge they are facing is the integration of the solar technologies in the industrial plant. My question is, it is only about the technology, or is also, for example, an issue related to how the projects are, prepared, so in terms of budget and so on? So do you see it as a barrier only related to the technology you are developing, or is something also related to how the project was conceived from the beginning?
Uli, will you go or shall I go?
I will start. So just answering briefly to Andrea's question, of course, if you are planning such a project, such a proposal, you do not know in that time what costs are probably approaching during the installation phase. And that's also something which, of course, also happens in our project, but also in others for sure, that with more costs, especially if you have to rearrange the installation site, which means if you're not allowed to install the collectors, for example, on the roof, you have to go beside the holes, the fabrication holes. There you have more installation costs for piping and so on. And those are things which are usually within such research and demonstration projects, you cannot really foresee that. And that is really a challenge at the end, how to overcome that within the project. That's for sure something which is somehow influencing such innovation projects. And I think, Giulio, you did a similar experience in your projects. Maybe you want to add something on that.
Yeah, in fact, for me, it's not so much about the project ship to fair itself, but it's about the sector. You see that we have a certain profile of production and a certain temperature of production. The way that the industry is structured today is really fully centered on the availability of fossil fuel. So they can turn the switch on and they, of course, as renewable heat action, we cannot really do that. So it's a matter of adapting to their way of working, their temperature. For example, just to give you a general consideration, almost all industries, they have a boiler producing steam and distributing steam across the factory. And this boiler can be 7 bar, 180 degrees, 10 bar, etc. But the reality is that all the applications, they don't need these high temperatures. They typically use 3 bar, 5 bar. Yesterday I was puzzled that all the machines were 3 bar. the whole system was a 7-8 bar system. So for renewable to reach this high temperature, it's not that easy. Of course, somebody can say, of course, the concentration solar can do it, but you know, there are specific conditions that you can do with concentration solar. And if you need to modulate your production, for example, from 3 o'clock in the morning to 12 o'clock in the afternoon, let me tell you that you cannot store that easily steam to use it later. So it's really a matter of changing their approach to generating energy from renewable and distributing this energy to be used at lower temperature and not necessarily at steam. So it's really a big change in mindset, and also a big change in the technology of the application machines, of the sterilizer, of the cleaners, of everything that is using this heat. So I guess this is the biggest challenge that I saw and that I'm seeing from now on.
Thank you both. Do we have any question from the auditorium? No. I only have one more question, mainly for Friendship and AZTEC, since they are low TRL. Of course, the time for the presentation was very short, but can you give a very short, hint about the main innovation you are proposing, since you are going for low TRL technologies? Which are the most innovative technologies you are developing and validating in your projects? Very shortly, please, 1 minute.
Well, let's as say there is 4 different equipments, but perhaps the more innovative are the combined heat storage. As I say, it is designed to store the heat from the solar field, but also from the industrial process itself. So it's like a dual. There is a dual mode of how to use it, and also perhaps the gas absorption chiller, which make it a multi-stage chiller capable to give cold down to -30 degrees C. And that's for Friendship. Let's see what AZTEC is doing.
Hello. I think I addressed it in the presentation. The 2 main innovations is the solar collector that is able to collect the energy from the sun in higher areas, like in one of the use cases in Romania. And the other one important innovation is the thermal energy storage using inserts and with certain types of salts. Those are the 2, and then of course the control system. But the main 2 developments are the solar collector and the phase change material thermal energy storage.
Thank you.
If I just can add something about the control, it's true that if, as we are talking about more about systems than just an equipment, there is also a strong, let's say, work on control, and it looks like, I think, sometimes innovation in this way. So.
Yeah, this is clearly one, I think, a cross topic for all the projects. So thank you all the presenters. It seems that we don't have any other question from the attendees here or even online. I don't know, Regis, if you are following. Okay, in any case, I mean, the time is very short, but if any question arises, I think they can directly forward you even by email, since all the contacts are reported in the presentations. So thank you again, and we can move to the next session, which is about solutions for renewable heating and cooling. Here we have a real hybrid session, since we will have 2 presenters here in Rome and 2 online. The projects that we are going to present are IBUILD, SWS Heating, Scores, and Ministor. So I will leave the floor to my colleague Valeria Palomba, who is presenting the IBUILD project.
Hello everyone. I will now present the IBUILD project. IBUILD project started exactly 4 years ago, in October 2017. And as you see from the schematics in the top part of the slide, it is a quite complex system that makes use of PCM storage, a thermochemical storage that are coupled together. Oh, yeah. And an electricity storage. All of them act together with suitable control logics to increase the share of renewables at building level for residential applications. 3 pilot installations have been put in place. So for the Mediterranean system in Almatret in Spain and in Aglancia in Cyprus, and for the continental system in Langenwang in Austria. The project was carried out in mainly 3 phases. So during the first years of the project, so before 2017, as Andrea and other colleagues already presented in the previous editions of Sustainable Places, all the main technologies were developed in the lab. So the suction module was developed by Fahrenheit, Micrometal, KG, and tested in our labs. And also by Daikin and National Technical University of Athens. The continental system was developed by AIT, Oxner, and again tested in the IT lab. In addition, PCM storage embedded with the heat pump was developed by UDL and installed in both systems. And at the same time, the electrical storage was developed by engineering and CSCM and our colleagues at CNR, and tested partially in Switzerland and partially at CNR. So let's say half Europe was involved in the project, making this really a European collaborative project. So before 2019, all the technologies were developed and validated at lab stage. Also due to COVID installation. Now, during this year, all the pilot site installation were completed, and the continental site in Langenwang has been run for almost 6 months, so from spring now. Moreover, all the environmental analysis and the social life cycle assessment have been completed, and life cycle costing is on the way and will be completed in the next few weeks. Whereas for future cases, so you see some pictures for the installation of the system, which is really nice because now the project is running towards its end, and it's nice to see that everything that was really developed is now in place and partly running. And to see that actually the results that we already got in the lab are really promising, that from both the energetic point of view and the environmental point of view, the system seems to perform well. So regarding the challenges that were encountered, the system is a quite complex system where a lot of components have been developed that require to be orchestrated together, which was a big challenge that was faced by all our colleagues. And due to the low TRL of the technologies, the cost is really high. And for continuous operation in pilot site, also reliability is an issue that needs to be validated and addressed. But at the same time, we saw that from this project, still a lot of opportunities come. So the system performed even better than we actually expected, and that it really has a high flexibility, which is crucial for the sector coupling and other applications that really represent the key of the next programs of the European communities. And it also proved to be a good example of how industry and academia can collaborate to really move from basic concept and basic research towards pre-commercial applications. Thank you.
Thank you, Valeria. I would like to welcome Claudia Fabiani from University of Perugia, who is going to present SWS Heating Project.
A little bit shorter than the rest of the speakers. Okay, so good afternoon, everybody. I'm Claudia Fabiani. I'm a researcher at Perugia University, and in these few minutes I will talk to you about this really compelling project that we are carrying out with our partners, which is the SWS Heating Project. The project is essentially aiming at developing an innovative seasonal thermal energy storage system, making use of a novel storage sorbent material and embedded in a compact multi-module system. And of course, in order to do that, we need to use together lots of different advanced components and also produce and use specific smart control strategies that are useful for our case study. The final aim of this kind of application is, of course, to store energy and shift its use, since it's a seasonal application, from the time where it is very more abundantly present, so summer, to the time where we have less energy, so essentially, of course, the cooler period. The team of the people that's working on this project is 15 partners of different from different parts and different origins, let's say in Europe. Of course, we have several universities, research centers, and companies. The main goals of this project, as I said before, is to develop a very complex system that can be integrated in new and existing single-family houses. And of course, this system should have some basic things to guarantee, let's say. So the first aim that we had was to develop a system with a minimum solar fraction of 60%, to reduce the cost of our system compared to competitive elements by at least 20%, and also to obtain a validation of the system up to TRL 5. And to do that, we had to produce a multi-level approach in order to analyze our system as a full element. As you see here in the slide, we talk about level 1, so the integrated system. And then we switch to the subsystem component and then down to the material scale. Main results that we achieved, the project was actually started in June 2018, so we've been working a lot in the project, but of course we had some troubles during the COVID-19 situation that produced some delays. In any case, we managed to produce the sorbent material that we were aiming at with all the characteristics that we were aiming at, and it was also, of course, tested at the ITAE labs. We were able to develop the configuration of the combined system, the multi-level system that we designed and used in this project. And we also developed and optimized all the components of this system. Main barriers that we had to face and the main challenges that we had to tackle within this project. Of course, first of all, we had to be able to put together different kinds of technologies, like in the IBUILD project before, which was quite difficult, and we had to define a dedicated control system in order to let them cooperate together. A second barrier, which is also very important, is the fact that we had to produce a multi-objective approach in order to identify and characterize our system and optimize our system. And we did that by means of dedicated key performance indicators that allowed us to judge the behavior of our system, both from a technical point of view and an environmental sustainability and cost efficiency and awareness point of view. Finally, the main challenges of this project, of course, the most important one was the fact that we wanted the system to operate at low temperatures. And of course, because we wanted the system to also being usable, let's say, in Northern Europe. So this is a main challenge. Final challenge, of course, the possibility to introduce in the system all the elements that we said before and produce something which is a configuration with high corrosion resistance, high durability, and low cost. Thank you all.
Thank you, Claudia, for the very nice presentation. So we now have the two virtual participants. The first one is Paul Bodis for the SCORE project. So Paul, yes, you're connected.
Good afternoon. Good afternoon. So my name is Pavel Bodis. I am a project coordinator, technical project coordinator from TNO for the SCORE project. And in SCORE project, if I can put the next slide, please. We are developing a similar system with a similar goal to the previous two projects. So thank you very much, guys, for introducing the topic so nicely. So I can move on to explain that in our case, we're looking at developing a hybrid energy storage system, both heat, electricity-driven system for houses for multiple family houses in various locations in Europe, similarly to your projects, where we apply a heat pump system, energy storage systems, and as well as demand systems developed by our partners. These are 12 partners with the nice logos on the bottom on the screen. Our goal slightly differs from the perspective of the users, where we're looking at to provide as much local flexibility and self-consumption potential for various technologies that we are testing. So the purpose is not to have as complex system as possible, but rather test which technologies under which configurations provide the highest added value for the lowest cost. If I can ask for next slide. The most relevant results that we have looked at are shown here on the picture. Obviously, in the middle, what you see are the demonstration sites where we have tested our systems. And one thing that we try to look at in our results is try to get as much of our prototypes into a phase where we can commercialize them. This is successful on two occasions, which are shown on the left and on the right side. One of them is a heliopack system that provides domestic cold water based on a PVT system generation, ground source, and innovative technology of control systems in multiple family houses in various configurations, mostly in France. And the second one you see on the right side is a breakthrough heat storage system, and sensible storage system for mid-term storage of heat on small volumes and small capacities for domestic use. Besides these, let's say, high-end and high TRL systems, we've also developed several low TRL systems, that one of them being a redox heat storage system that is we discovered is much more efficient to be used in large-scale applications. Think of district heating systems. If I can go for the next slide. In this slide, I try to show you a little bit the challenges and barriers, of course, of what we've encountered in the project as well as on the market. And besides the issues mentioned regarding COVID and installations of the system, it caused for us also quite significant delays and issues in the system integration. What we see from the market perspective are obviously strong regulation challenges about implementing new systems. As I mentioned, one of our systems, the redox heats, using hydrogen as one of the sources, and let's say implementing hydrogen solutions in the built environment remains to be a big legislative challenge. From the perspective of economic challenges, we see on one hand a relatively conservative OEM suppliers for adaptations of various innovative solutions. They like to stick the things that they already make and sell what they can sell at as lowest cost as possible, not looking so much into how the new technologies can improve the performance and energy efficiency in buildings. On the other hand, we see the complexity of the stakeholder management in the innovative projects where all neighborhoods are taking place, and their local municipalities, grid operators, owners, tenants are playing a certain role, and then who is taking the costs and who is taking the benefits for all the systems is still a puzzle to be solved. Thank you very much.
Thank you very much for the presentation, Paul. So nice points of discussion, I guess. And then we move to the last presenter for this session, who is Carlos Ochoa, who is the coordinator of the Minister Project. So Carlos, I don't see you, but yeah. I guess you're connected. Okay, please.
Yes, I'm connected. Thank you very much. Hello from Ireland. My name is Carlos Ochoa, and as mentioned, I'm the coordinator of the Minister Project. Next slide, please. The context of this project is that we have to use thermal energy storage in order to improve the building efficiency. And for this we took part in a competition from the Horizon 2020 project that was requiring advanced thermal energy storage. That among the goals, we wanted to significantly reduce the energy consumption, have high stability and high performance, which means 10 times more than the storage capacity of water. So therefore, the approach that was used is what you see on the far right, a system that uses PVT photovoltaic thermal panels for generating the electricity and heat. And then this heat is then placed into both an electrical battery or a thermochemical reactor. This thermochemical reactor is activated by ammonia gas in order to reduce the corrosion. And then we can generate both heating, cooling, as well as electricity to the household or to sell it to the grid. Then this system has been developed through a consortium of 18 partners, and the coordination falls on the International Energy Research Center, which is part of the Tyndall National Institute. Next slide, please. Among the results that we had in 2019, the project started. During 2020, even though we had the COVID-19 pandemic, we could do a study of market constraints, define the key performance indicators, and provide the first calculation for this design. And then during this year, we have managed to do baseline monitoring of the demo sites and to finalize the system design. And next slide, please. Among the barriers and challenges, one of the main barriers are the regulatory ones, since they are more for industrial applications and not for residential ones. So the system can be made very safer than a usual gas stove, but this comes with a price, which is barrier number 2, that provides a high initial cost, and also there is a lack of knowledge on the potential benefits of the technology. This provides some challenges that we have to exploit the material properties through safe and reliable implementation. This means being very careful that there are all the system constraints are met, and as well as the security requirements are met as well. Challenge number 2 is the integration with buildings. Due to the same regulatory barriers, the system can only be placed in specific places. And then also we need the scaling up that can allow an acceptable cost, as well as building the consumer confidence so that they know that the system is safe and can be implemented in a way that can be used by everybody. And this is my presentation. Thank you very much.
Thank you. Thank you, Carlos. Mm-hmm. Can you hear me?
Yes.
No. Okay. Good. So we have, yes, a bit more than 5 minutes to discuss on this topic, on storage. So I would like to start both from Scores and Minister, because both Paul and Carlos were reporting that regulatory barriers are really important for implementing storages technologies. If I'm not mistaken, SCORS is also low TRL, so I guess they already started thinking about these points, while Minister is a bit higher in TRL. So I would like to ask you, which are these barriers? I mean, which are the regulatory barriers that we are facing in these projects?
If I can start
Yeah,
from
please.
SCORS project perspective, we've encountered two main barriers, and one of them related to use of hydrogen in and around built environment. Hydrogen is, generally speaking, a technology that is meant or is often was used in industrial applications, and there is effectively no legal framework that guides in how and in which way you can use hydrogen. Not looking into a safety itself of the system that use it. Simply put, gas is okay, but hydrogen is not in most of the situations. So that is that's one challenge, so lack of legislation. And the other one is regarding electrical batteries. As you may know, in many countries around Europe, there are already legislation put in place to prevent electrical batteries to be installed in homes, and as to be placed outside of home in special containers. This significantly increased the costs. And I think this is a challenge for the whole overall industry, whether those are, let's say, new electrical batteries or second life electrical batteries as we use them in our systems. It's becoming harder and harder to find situations where they will be applicable. So this is a challenges that we've seen.
You, Carlos.
Yes, in a similar way for the Minister project, what we have found is that there are standards existing for the application of ammonia, but they also restrict where the system can be placed. And of course, why is this done? Because it's mostly thought for industrial applications, which have a lot of quantities of this gas. So therefore, this also limits how we can apply the system. Of course, also, as Pavel said, you have less restrictions for cooking gas than for these systems.
I would like to ask, if possible, Valeria and Claudia to come just, I don't know, of course, if there are some questions also from the speakers, you are welcome to make your questions. I mean, I know both IBUILD and SWS eating quite well, but I saw that both are facing issues with the cost. So I would like to ask both Valeria and Claudia to shortly describe which are the main components or technologies that are showing high capital cost compared to, let's say, the state of the art, if possible.
So for the case of IBUILD, the main costs were associated with the desorption technologies that is still, I mean, not so, it's still a niche market, even though there are some commercial systems, and for the components for the PCM storage, because still everything needs to be customized. There are no, let's say, more or less standard or reference components that can be used, and this is probably one of the direction in which the research should go in the next year. So creating a set of components specifically designed for these applications that are already ready for even small batches industrialization, and that can reduce the capital cost of the system.
Yeah, very similarly, I would say, in case of SWS heating, we are also dealing with sorption materials and sorption technologies, which are quite expensive because of the state of the art in these kind of applications. But we also found particularly compelling the part of control strategies. Producing a smart control is never that easy and can be very costly, especially when you try to combine different kinds of elements in your system. And this is also true not only from the main economic point of view, but from the maintenance and the use phase point of view. I mean, a good control strategy can allow you to reduce the cost of your system in the long term, let's say, because users can, let's say, afford to know less about the system if everything works properly. And this is very important, especially when we are considering systems with different kinds of technologies all combined together that need to settle together properly. And the user, of course, cannot be expected to know how everything works, how everything is compelling together.
Thank you both, Claudia and Valeria, for the answering. I don't know if we have any other question.
I would have a question, if I'm allowed. I'm Danny Carbonet. Yeah, okay. So this is a question for all that work with like high energy density storage or thermochemical especially. Can you tell us the value of the volumetric energy density of the storage solutions when you consider everything, like all your storages for charge and discharge? So the complete unit, what you need in volume, if you compare this to water, what is the real kind of benefit? Because we always hear like numbers about materials, but materials is just a small part of the whole thing. And I would be interested to know the real number of it. Thanks.
Pavel or Carlos, would you like to start answering? I think all these projects are dealing somehow with desorption or thermochemical, so this is a question for all of us, all of you, actually.
So maybe from the scores perspective, first of all, the redox heat system has a target energy density on a system level, on a product level of 1.2 gigajoules per cubic meter. In practice, we've seen that this is a very hard number to reach, and we will end up with somewhere on 0.7, 0.8 at costs that are prohibitive for applications in some small scale. That's why my comment was to go to large scale where the cost will go down, and also the safety restrictions go down. On the TCS system perspective, which is not related to scores project per se, but to other projects within the same group, what we have reached on a system level, and we are looking into spinning out that technology into a company, we've reached already 0.4, 0.5 on a system level, and we see possibilities to go on system level to 0.7, 0.8 gigajoules per cubic meter.
Thank you. Carlos, did you already make some calculation about these numbers?
Well, if I'm not interpreting incorrectly Daniel's question, the system has been designed, because it's for households, for a capacity of 30 kilowatts hour. But if I'm not that familiar with the number, I can also give you more information.
Thank you. Any answer from IBUILD and SWS, please? I can help you maybe. Please.
I don't remember the exact value that we reached with our system, actually, to be honest. I think the main challenge was reaching the 60% of solar fraction of energy use for our system, especially because we were aiming to reach that value for northern country in Europe and do that at low temperatures. This was the main focus, let's say, from that point of view.
Yeah, I may also add something since I'm also involved in SWS Heating Project. Basically, first of all, if you want to make this comparison, you need to consider, at least in our project, we are targeting seasonal storage, not daily or let's say short-term storage. So water is of course the real competitor, but it's also true that if you look at long-term storage, water is less attractive, and so also making the direct comparison of storage density should take into account the losses that you encounter in long-term storages. I will say that for SWS, we are now going to test in the lab the technology. We expect a storage density similar to the one that was mentioned by Pavel, so something like 0.5, 0.6 gigajoule per cubic meter. That's what we are aiming at reaching in lab, which is more or less half of the one that you can get at material level in the end. I don't know if Valeria wants to add something.
Well, for the case of IBUILD, it was a bit different because the idea was to optimize the whole operation of the system, which means that rather than focusing on increasing the storage density, what we aimed at was to make the system as flexible as possible in order to increase the self-consumption. And to have enough heat transfer capacity to supply sufficient energy, especially in the case of the continental system that is meant, in which the storage is meant for domestic hot water production. So from the simulations done so far, it seems that by charging the batteries, so the electrical storage with PV and suction module, and using the low temperature storage for the heat pump for storing energy. So by charging them during solar hours, so during the day, it's possible to run the system without any external primary energy source during the rest of the day. And that was the result we were aiming at, rather than increasing or having a system with high storage density.
So thank you very much. I think we need to move to the next session because the time is very short, unfortunately. But again, I would like to ask all the attendees and also the speakers, in case of any other question, to direct contact the project's presenters. So we are now moving to the third session, which is the one, about low TRL technologies for renewable heating and cooling. So basically, we'll have 4 projects presenting here: Innova Microsolar, Solbiorev, 3HP, and Rest for Build. As you will see, all these technologies are, of course, working on new renewable heating and cooling solutions for mainly for buildings, I would say. So the first presenter is Dr. Luca Cioccolanti, who is going to present the activity of Innova Microsolar. So please, Luca, the floor is yours. We cannot hear you. No, we don't hear you at all.
Okay, can you hear me now?
Now, yes, yeah, please.
Hello?
Yeah, now we can hear you. Please, Luca. No?
Hello?
Yes, Luca, you can go ahead.
Sorry, I didn't hear you. Good afternoon all, and thank you, Andrea, for inviting me. I'm Luca Cioccolanti, Associate Professor in the field of System for Energy and Environment at Universitae Campus in Italy. Today, please, Andrea, today I'm going to briefly present you the Innova Microsolar project, which was proposed within the energy efficiency call in 2016-2017, dealing with the development of an innovative, high-performance and cost-effective 2 electrical kilowatt and 18 thermal kilowatt solar heat and power system for its application in residential buildings. The plant aims at providing about 60% of the energy demand of the building, and at the same time reduce of about 20% the CO2 emission compared to other renewable energy technologies existing in the market. So in the project, we work in the design, developing, and testing of this innovative micro combined heat and power system, which mainly consists of about 150 square meter area of linear Fresnel reflectors, of an organic ranking cycle unit coupled with an innovative latent heat thermal energy storage, which is equipped with reversible heat pipes in order to improve the conductivity between the thermic oil and the phase change material, thus improving the energy efficiency of the system. The project is carried out by a group of 3 European universities and 6 small-medium enterprises across 4 European countries, and is coordinated by Northumbria University at Newcastle. Andrea, please skip the next slide. So the project started in September 2016 with the design phase of the main components and the development and their testing at the premises of the small-medium enterprises which were in charge of the manufacturing. At the same time, other partners performed some preliminary evaluation to assess the potential of the system compared to other existing technologies targeted for the residential buildings. And in 2018, we were able to install the system in a relevant site. Indeed, the scope of the project was to bring the subsystem and the overall plant from a TRL of about 3.4 up to 5.6. So we installed the prototype in site in the municipality of Almatret, which is not far from Lleida in Spain. But since the very beginning, we experienced some issues related to the reliability of some component and to the failures of some of them, and in particularly of the ORC system and the turbo expander that was designed to operate at quite high operational speed, I mean in the range of 30,000 rounds per minute. This means that part of this subsystem had to bring back to the premises of these companies to further develop the system and perform several trials both in their premises and again the relevant site. And this takes a lot of time and forced us to ask for a first extension. Unfortunately, restriction due to COVID-19 pandemic further stress these issues, and we were forced to further extend 1 year more. So the project is expected to end in June 2022, and it is expected that since now on, because some of the partners are there in these days to performing the hot commissioning of all the components, to perform an extensive test campaign in order to test the system in different operating conditions and also assess the influence of seasonalities in order at the end to re-engineer some of the components. Andrea, please. As I have mentioned you, we have faced and are still facing some technological barriers due to the development of such technologies at a very small scale, and which in particular for the turbo expander is very challenging. Another challenge that we face, apart from other challenges related to the development of the project, was, as for most of us, the restriction imposed by the pandemic, which makes not possible to test all the components according to the time schedule. But in terms of challenges, the two main challenges are related to the expected performance in terms of energy conversion of the components and of their reliability. when I say that it is not only related to the RHC unit, but also to the thermal energy storage system. And also the other challenge, very significant, is related to make the system cost competitive. Indeed, why it is possible with respect to some of the subsystems involved, like for example the solar field, that in case of mass production can be cost competitive with other technologies. We cannot say the same with respect to the latent heat thermal energy storage that we are considering in the present configuration. So if we consider it compared to other technologies, we are far to be cost competitive in this sense. Thank you for your attention. That's all from my side, but if you have further question or some curiosity, I'm here and glad to answer you.
Thank you. Thank you, Luca. We will have time to discuss in the end for sure. So we now move to the next one presenter, who is Professor Sotirios Karellas, presenting the SolBioRev project. So Sotirios, the floor is yours.
Thank you very much, Andrea. I would like to say hello to everybody and welcome you to my presentation. It's a pity that we are not, I hope this is the last time for sustainable places not to be everybody in one room. Let's hope that next year we'll be all together and have some interesting discussions also during the breaks, etc. So SolBioRev is a project dealing with reversible energy systems for converting a large share of energy needs in buildings. The coordinator is the National Technical University of Athens, and it is a project that has started 2 and something years ago. So the project, the main concept of the project, please go to the next slide. The main in the project we are partners from various areas of Europe: Greece, Italy, Spain, Germany, Belgian partners, and Austrian partners. And the idea is to use mainly 2 renewable energy sources, solar energy and biomass, for covering heating, cooling, and electricity demand of buildings, residential and commercial, by integrating the innovative technologies. And what is our aim is the development of innovative technology systems and integration by means of advanced control. Very, very important. It was also mentioned before regarding the control. Renewable energy sources without the appropriate control, without the appropriate integration of the control and the development of the control is not possible. And in order to reach high renewable energy penetration in the buildings, we need to have advanced control. So system validation through 2 pilots that we are going to have, one in Germany, one in Greece. So we have so nowadays we have the lab development, we have tested several subsystems, and now we are in the phase that we are trying to finalize the testing of the subsystem to realize the control and to start thinking about the pilot testing in Greece, in Athens, and in Germany, which is in Nuremberg. So, as I said before, 15 partners from SMEs and RTD partners from all over Europe. And I forgot to say UK before. UK is also a partner in this consortium with the University of Sussex. Yes, please, next slide. So here is a concept. The concept is actually to have, as I said before, heating, cooling, and electricity coming from mainly the sun. In the summer mode, we have thermoelectric generators that are providing directly electricity. We also have a storage tank that gathers all the heat from the sun. And then we have a reversible heat pump ORC system that, according combined with a chiller, with an adsorption chiller, and according to the needs of the building, we can work as a heat pump, so producing together with a chiller producing cooling, or as an ORC producing electricity. And in the summer, domestic hot water is coming from the storage tank. On the other hand, in winter mode, we have more need for heating, and we have need for electricity. In case we need some more heating, then there is a biomass boiler that is being optimized, and which can also provide heat if needed for the organic ranking cycle. So, and the Sol BioRev system overview can be seen in the next scheme. Here is an overview on how we have it in our mind. Heat coming from the sun, as I said before, cooling, heating, and the cascade chiller heat pump for the production of cooling, and electricity when the heat pump is working as an organic Rankine cycle. What are now the challenges? What are the barriers we can see in the next slide? First of all, we need to see the relevant results. The system potential, so domestic hot water is coming 100% from renewables. 70 to 90% the renewable energy sources share for space heating, 100% renewable cooling, especially in Southern Europe, which is needed, and up to 60% renewable energy share in Northern Europe. The development, we have development in subsystems. In the biomass boiler, notable emissions reduction, the thermoelectric generators, we need to have efficient operation of them together with the solar collectors. We need to have a heat pump ORC using the 1234 ZE. And finally, we have started developing the pilots. In Athens, the pilot is already built, and I will be very happy if someone from you comes in Athens together with Professor Foodie, who is going to present Plural afterwards. We have built a pilot, and it is very interesting to have a look. So if you come to Athens, please come to us and we can show it to you. And the system design. So barriers, technological barriers, heat pump based system operation under various conditions. This is very interesting, how we can really work with the heat pump and also change it to the ORC way of working. Economic, we have high cost. I remind you, we have a low TRL project, so that means that for the moment we have a high cost of the subsystem and the integrated system. What are the challenges? That the stakeholders understand the system that they are engaged, and they due to the complexity compared to conventional systems, so that the people can understand the technologies. And of course, the integration in buildings, installation, maintenance, and retrofitting needs, and how this will be carried out. So I think I have one last slide, or this was my last slide. Please, Andrea, the next one. No, this was my last slide. Many greetings to everybody from Athens, and hope to see you all live soon. I'm very happy that Daniel speaks after me. Thank you very much.
So now is, as Sodiris already anticipated, it's time for 3HP project presented by the coordinator, Dani Carbonell. Please, Daniel.
Thanks, Andrea. So hello, everyone. So yeah, I'm the coordinator of 3HP. This project stands for generation systems based on heat pumps with natural refrigerants and multiple renewable sources. If you can go to the next slide, please. So the main goal of the project is to develop systems that can deliver heating, cooling, and electricity to multifamily residential buildings. And we are doing this using electrically driven natural refrigerant heat pumps coupled with photovoltaics. And our main target is to achieve a 80% renewable on-site share with a net zero energy concept, and having systems that can reduce installation costs between 10 to 15% compared to current technologies with the same efficiency. And this will end up reducing 75% the greenhouse gas emissions. If you can go to the next slide. So I will just show one of the examples of our systems because time is short. So this is what is called a solar ice slurry system. In general, what is known as solar ice is a system that uses a heat pump where the heat source for the heat pump in the evaporator, it comes from solar thermal collectors. And in order to compensate time periods where you don't have enough energy, like say night or cloudy weeks, we use a water storage that will eventually ice in winter. And because ice, it's at 0 degrees in winter, soil collectors increase their efficiency a lot and can regenerate that storage a lot. And our innovation in this project is to use an ice slurry concept, which means that we can eliminate completely the heat exchangers inside the ice storage, reducing the cost by at least 10%. If you can go to the next slide, please. So in the project, we have developed a lot of components and also materials. First thing we had to do is to develop isophobic coatings for our supercooling heat exchangers. This is already done and working in operation. Then we also developed 3 kinds of heat exchangers for heat pumps. One is a dual sourcing heat exchanger that is able to use brine and air as a source for the heat pump with a direct exchange with the refrigerant. This also has been done. Then another development is a supercooler using these isophobic coatings developed within the project. This is also completed. Next heat exchanger was a tripartite gas cooler for a CO2 heat pump. This is also done. And these heat exchangers have been integrated in 3 heat pumps. And we already built and tested successfully the first prototypes, and now we are testing the second prototypes of all of those. One is a propane heat pump that it's a reversible heat pump that can use this dual sourcing heat exchanger, so you can use brine and air as source and sink for heating and cooling. Another heat pump is a propane base for this ice slurry concept using the supercooler. And the third heat pump is this CO2 using a transcritical cycle with an ice slurry also concept using the supercooler and the tripartite gas cooler. So the second prototypes are built and we are being tested now. And then we have on top of this an advanced energy management system, so a control system for the complete system, including a model predictive control and also for the fault detection. The fault detection is done and the advanced energy management system is ongoing and will be tested with a complete system. So when we finish the testing of the heat pumps, we will test these heat pumps in a system environment, what we call hardware in the loop test, where the heat pumps plus storages, ice storages, crystallizer, pumps, hydraulics and controls are physically installed, and the rest of the system is emulated and simulated. Let's say PV, solar thermal, ground source, all this is not installed in the lab. And with this, we can emulate real conditions. If you can go to the next slide. I will just show you one key result of the project because we have many and there is no time. And this is our development on supercooling technology. Just shortly, I mean, for those that are not updated on this, so to say, on the right, you can see this graph of the supercooling kind of process. So we can have water that we can cool down below the melting temperature. This is what is called supercool water. And this supercool water at some point will crystallize, releasing all latent heat. The supercooling temperature is the difference between the melting temperature and the actual crystallization temperature. And the challenge here is to use heat exchanger, industrial relevant brazed heat exchanger that we use in standard heat pumps that can supercool water in a stable way. And for this, we use these isophobic coatings. And we have achieved massive progress beyond the state of the art, reaching supercooling degrees up to 4 Kelvin on a stable form, which is twice as current state of the art systems in Japan. If you go to the next slide. And in terms of barriers, basically, we had COVID-19 like all of you, and in our case we have a lot of development on the lab. A lot of heat pumps have to be built, so it's a lot of material to be requested. So we had a large delivery times, so this delayed our work. But we had a good work plan, I would say. So we had enough time to kind of solve these delays. And so we have shifted things, milestones, and this like this, but we hope that the end of the project will stay as it is. So we are optimistic that we can even handle upcoming delays. Another problem was one heat pump manufacturer could not support this COVID thing and went bankrupt. So we had to handle this, and we did this internally in the project. So the other heat pump manufacturer, together with the research institute, took over the responsibilities of this partner, and this worked very well. So we did not have the need to look for external partners. This was very good. And other barriers are, well, technological barriers. We had a lot of them, but up to now, we have managed to solve them all. And for this, I would like to thank the whole TriHP team, because it's a great team. And we will see the next ones. I mean, we still have a year and a half to go with some still technological barriers to solve, but we hope we can handle all of them. And yeah, that's it. This is our consortium. And yeah, we can discuss later on.
And now move to the last presenter for this session, who is Miguel Papapetru. I hope it was fine. We is going to present the project RES4Build. Please, Miguel.
Yeah. Thank you very much. So I will talk to you about the RES4Build project. I'm here, I'm the coordinator of the project, but I'm here on behalf of the whole consortium that we work together in developing this project. We're 15 partners from universities, research institutes, small and large companies from all over Europe, spanning from Scandinavia to the Balkans to Poland to Central and Western Europe. So I'll move to the next slide, where we present the overview. So similar to the presenters before me, so Lucas, Dani, Sotiris, we are also trying to deal with the challenge of decarbonizing energy in buildings. We do take electricity into account as well, so we try to present at the building level solutions that cover as much as possible, up to 100% or even more, for exporting extra energy at the building level. So on the building side, to have technologies that can cover the whole electricity and heating and cooling needs. But our main focus is on heating and cooling, because for electricity needs, there are solutions in place, there are commercial solutions that apply today. For heating and cooling with renewable energy as well, there are some solutions, but it's a more complicated project problem, and that's where we're mostly focusing. So it's not very big maybe on the screen like that, but on the bottom right, it is the schematic of the project. It's a simplified schematic. But what I would like to highlight looking at that about our solution or our approach is the different sources of heat that we use. So there is solar heat, first of all. We have PV thermal collectors. So we take heat from the sun. Then there is the ambient heat. In the heat pump, we use also the ambient heat. And then we take from the ground. From the borehole thermal energy storage, we can take heat from the ground as well. So we use different sources together for the heat. And at the heart of our system is the multi-source heat pump. And this is powered by solar electricity, so the PV thermal collectors. To the extent possible, we power with solar electricity the multi-source heat pump. This is the basis of our system. And then we have the building energy management systems. All previous projects mentioned the control. So we also have here the control. We develop algorithms to optimize the overall system, because with many sources, it is very much about optimization. But I would say here also the Vito works on the control and optimization, and it's also about forecasting the weather, forecasting the consumption, but also using the passive storage within the building. So by calculating for each building and artificial intelligence learning the building, how fast it heats up and how fast it cools down, trying to use, when needed, this storage on the inertia, let's say, of the building, the thermal inertia of the building. So if we move to the next slide. So we start from between 2019-2020. The main focus of the project, it's a low TRL project. So the main focus was on developing the components, the different technologies, the most innovative parts of the technologies. So we have the PV thermal collectors. So the focus was on developing prototypes and testing the prototypes of this advanced design of the PV thermal collectors. They're from Sweden, and they were optimized to work there. So they've changed them to optimize them to work also in different latitudes to maximize the overall energy over the year. And then we have the magnetocaloric heat pump. So part of our heat pump, we work with a vapor compressor heat pump, but combined also with a magnetocaloric heat pump. So this is a prototype has been built and has been tested. So this is quite innovative, and if for a magnetocaloric heat pump, it has been operating better than any previous magnetocaloric heat pump. And then we've moved also. We have the algorithms and the optimization. We work in parallel on life cycle analysis and so on, but we have a work package on co-designing. So we have several case studies. I have to mention our main focus is large buildings. So we work with multifamily buildings, offices, but also shopping centers and so on. So we work in several case studies in Poland and the Netherlands mainly to work with end users on what are the characteristics of the system that are most important to them, how is cost, and so on. And now we're moving to the last phase of the project, so the second half of the project. We are building at the moment the prototypes, so integrated prototypes. We have developed so far prototypes of components. Now we have integrated prototypes with a full system I showed you at the first slide. We have one in Greece and one in Denmark with a full system. And then we have two in Belgium with smaller systems where it's more the testing of the control and the borehole thermal energy storage. So if we move to the last slide, it's about the barriers and the challenges. I'd say this is similar to everyone else. So I would like then maybe to take a minute here about the barriers to talk about how complicated the system is, because I think a common element we also have in all our projects. We are presented, let's say, with call topics for European funding, and we come up with solutions and we do these interesting projects. But one, I think, common element among many projects is we develop quite complicated solutions. And that's a challenge for how they should be applied in reality. I do think that here, us by focusing on large buildings, it helps on the one side, because if you are to have a complicated system, it's probably better to have it scaled up, have it in a large building where you can have professionals dealing with operation and maintenance. But on the other hand, you have the barrier we mentioned here. When you are in large buildings, it's the decision-making process is a bit more complicated. This is what we find in our co-design process. Who decides? Does every owner of every part of the building agree? Or sometimes what we found is that owners of large buildings like shopping centers or office buildings might be like investment funds from the Middle East, and they don't care if the heating system is natural gas based or more efficient or lower operating costs for the tenants and so on. So this type of barriers rather than the technological, I would like to highlight, and that's all from me.
So we have more or less 5 minutes before the coffee break to discuss. So yeah, I shared the comments from Miguel that in the end, what is clear is that most of these technologies, also because they are from, let's say, starting from low TRL, but the main challenge usually is that they are quite complex and difficult to bring to the market in a short time. Surprisingly, I will say Danny was not mentioning this part in his presentation. Danny, can you comment on this? Did you face something like this or not?
Well, I mean, we will not face it yet because the system cannot be installed yet. So we have a work package on social acceptance where we look at all these issues, non-technical barriers. But from what we see, like our system, Solar Ice system, is a system that it's been very much established in Switzerland because it's a system that can compete with the ground source with the benefits of not having to regulate with water protection laws and so on. So this system is being installed despite of the actual higher cost than ground source and higher complexity. So this is already kind of, this barrier is being now faced now. What we come up with a system is to reduce the cost. And of course, we add some technological kind of complexity on our side, but this, if we solve it technologically, they won't see it, because the heat pump will be a normal heat pump with a evaporator that will do something they don't see. So it's not something different from them. And of course, then we need a nice crystallizer and then a storage that it's just a casing with a slurry on it. So the technology, so the social barrier is already now in place, and they are kind of working with this, and it works, and it's been growing in Switzerland quite a lot. So for us, this if we manage the technological barrier, at least I think we have a good chance to get into the market.
Okay, I have just one other comment. I will say it seems that most of these technologies, these projects actually are based on heat pumps technology, and I saw that most of you are using natural refrigerants or low GWP refrigerants. Do you see these technologies to reach the market quickly? I mean, of course, most of them are already on the market, but the ones that you are developing, so the novel components and so on, do you see they will be applied quickly, or they still need to be optimized and scaled up to the right TRL? I don't know. So Iris, Miguel, I think
I can answer to this. It is clear a heat pump is, I think, a technology that we all agree it's a very successful, let's say, technology for heating and cooling, because due to the high COPs and to the very high efficiencies. So if we can build, have as a base heat pumps, and we can build innovative technologies around the heat pump, this will create, so we steal a little bit from the high efficiency of the heat pump, let's say, for the new technologies. In these low TRL projects, we have some components that are very low TRL, but also are some components that are not so low. So I think that according to the needs of the buildings, according to the smart, taking into consideration a smart control system, and trying to use the absolutely needed components, you can reach the market for several geographic areas of Europe. And unfortunately, the very low TRL components that we are using need some time to be integrated in the rest. But still, I see some components that are quite high TRL, and they could be integrated in around the heat pump technology. At least this is the case for my project.
Miguel, do you want to add something? Very short, please.
If I may, yeah. As I said, we do have the magnetocaloric heat pump. This is for further in the future, hopefully. It's not going to reach the market soon. But as Sotiri says, the overall system can work without that. For the vapor compression heat pump, the low GWP refrigerants, it's still, I'm not the expert here, I think Sotiris, or the others maybe know much better, but it's still a trade-off. The efficiency will go slightly down. It's still acceptable, and it's a trade-off. I mean, if you increase a bit the GWP potential, you can have higher efficiency. But as long as the electricity comes from renewable sources, I think it's okay. We've made good experience with a very low GWP potential refrigerant we've used.
Thank you.
Maybe I can shortly add. And in our case, we use propane and CO2, which are very well established refrigerants for industry. So the challenge there is not that much technological, is to find the right components, because you need the compressor of this size and these kind of things. And as soon as you find them, then for a heat pump manufacturer, it's not a big deal to have something that can go into the market.
Yeah. Good. So thank you all.
Just one comment. We need, however, to increase the visibility of such new innovative systems, especially you mentioned, Andreas, heat pumps with natural refrigerants. And for this, we have accessed a service from the EU Commission. It's called Horizon Results Buster, and we'd like to invite also the other projects to cluster together, to join our forces, and make these innovative solutions for renewable heating and cooling more available to a larger audience. It's a free service, so if you are interested, you can just get in contact with us from 3HP. That's all.
Thank you, Miguel. Okay, so we now should have 10 minutes break. I think we need to short down to 5 minutes because we are a bit in delay, and we have a session right after this workshop. So we will be back in 5 minutes. So 4:30, we will start with the ITRL session. Thank you all for attending so far.
Thank you, Andrea.
Thank you for having us, and great organization.
We are now back to the workshop. We are going to have the only session fully in presence. So I would like to, it's about ITRL technologies for heating and cooling. We'll have 3 projects presenting. And the first one will be is GeoFit, which will be presented by the coordinator and also the organizer of Sustainable Places, Tom Messerville. So please, Tom.
Great, thank you. Thank you, Andrea, for the organization of the workshop, and thanks for the opportunity to present GeoFit today. We're running a little bit behind on the session, so I'll be fast. The project is GeoFit, deals with smart geothermal systems, and the context of the project is that geothermal energy has great potential, but that potential is not being fully realized for a series of barriers that we address in this presentation. So the approach of the project is to develop a holistic and novel approach to geothermal retrofitting, which is cost competitive, easy to install, and provides low temperature heating and high temperature cooling. So the goals of the project are to just that, break the barriers to geothermal and have more implementation and move to smart geothermal systems. The team is made of 24 partners across 10 EU countries, and R2M has the pleasure to coordinate this project. And the images shown capture the spirit of the project, that it is a holistic approach that does everything in the value chain, from the heat exchangers in the ground, the systems to dig, the survey before, the couplings with the heat pump, the couplings with the in-home heating systems, and the controls and systems to operate those systems optimally. Relevant results of the project. In very simple terms, in 2020, we've done our technologies and experiments, and it's a project of that whole value chain. So there's 17 or 18 very nice technological results. They are on our project webpage. Some of them that you see on this slide include survey systems for in the ground. We have structural health monitoring of the structures with georadar systems and vibration techniques, various drilling methods and improvements to the drill bits and studies about them, studies related to the heat exchangers in the ground to understand how these slinky systems transmit and capture the thermal energy, so that non-standard systems can be more widely employed by engineering professionals. In 2021, we're completing our pilot implementations. In Perugia, we see a BIM model to the bottom left of the screen of the building where that system is implemented. We see a hybrid heat pump here. We see an experimental station. We've done some 300 experiments of different configurations of slinky systems and basket technologies in different soils to understand how those perform. And then in 2022, we'll move into the pilot assessment phase, so how these pilots perform and the replication models and business models around those. And showing those results, I'm leaving out others because of the room available on the slide and the room available in 5 minutes. So again, I point to the project webpage for some of the results we have. So barriers and challenges, what I wanted to highlight on this slide was if we have this long chain of activities and skills that are multidisciplinary to put together a project, we need a design process that's different. And one what we focus on in the project is integrated design and delivery services. That's different than how projects are currently bid and contracted. And our technology and geothermal experts, they remark that by the time they get involved with the project, the decision's already made, and those decisions are not optimal. and they try to input into this decision-making process, but they have very little input at that point, or they have to undo work that's already done, and this is not optimal. Barrier number 2 is a lack of tools and knowledge and roles that can plan, design, and implement holistic, multidisciplinary projects. And what's intended there is, it's not just the geothermal system. You need a drilling expert, you need a heat pump expert, you need an in-home technology expert across all of the optimal systems that you'd like to put in that building. And we lack professionals that are comfortable with putting that all together. And this is I would like to say it's a new role, but it's not new, but it's certainly needed. And then for the challenges, I focus some on project implementation. One of the challenges is proposal writing. So any proposal has limited time and resources to do that. And maybe one writes installation works 50K. But this is a very risky approach to what's typically available. It's just not optimal. So because our proposal writers, they're not familiar with the different stages of bidding or contracting or implementing activities in the field and all the considerations that go into that. And this ties to challenge number 2, which is this role that is often not appropriately considered in a project, which is the pilot leader or the pilot work package leader, the scientific and technical manager. So implementing these pilots across multiple countries, multiple different types of buildings that have different rules and regulations and processes for contracting is not a role to underestimate in any project, be it whether it's in a research project or in a field project. So those are 2 challenges that I would encourage everyone to pay more attention to in the development phases of any project. And thanks for your attention.
Thank you, Tom. It's now time for Sun Horizon project. It will be presented by the coordinator, Federico Cruni from Reina Consulting.
Hello, everyone. Thank you for the wonderful presentations that were shared before. I will explain today the Sun Horizon project in this session. Sun Horizon means Sun Coupled Innovative Heat Pumps project. So as you can imagine, it's focused on the combination of solar technologies with heat pumps. We will start by explaining a bit the context. The context of the project is to help reducing the technical and market barriers that we know many of these innovative technologies, and especially the integration of innovative technologies, still have on the market. But also to evaluate, to better assess their performance. And the approach of Sun Horizon is to demonstrate the coupling of heat pumps and solar technologies in 8 different demo sites across Europe. Actually, there are 9, because we have 2 single houses in Riga, which we count as 1. And the goal is to both reduce system costs, but also improving performance. In fact, one of the barriers of these technologies is usually the cost, as well as the assessment of the performance, because it's not easy to finance this combination of technologies. So here you can see that the partnership is quite large in the project. We are 21 partners. And actually, because I wanted to make this presentation short, I kept out some of the slides that I think would be useful to explain what are the demo sites. So I need to show them to you now here in the map. Starting from the right, we have the Latvia demo sites, or led by RTU. We have there 2 single houses. Moved to Germany, we have 2 demo sites. One is in Berlin, another single house, and then in Nuremberg, we have a multifamily house. Then we have Belgium, where we have a swimming pool, so a tertiary building. We go then to Spain, where we have 3 demo sites. One is a tertiary center, a civic center, let's say, and one is a single house in the Barcelona area. And we also have a social housing complex, so a large multifamily building again. And this is about our demo sites. But the partnership, as you can see, is multiple and involves a lot of technology providers, around 6 technology providers. And they sum up and have technology packages. So the project proposes 5 technology packages, of which only 4 are actually installed in these buildings that I mentioned to you. And I can go to the next slide. Here we explain a bit of the main project results. In January 2020, so when we were at month 15 of the project, we prepared the technology specification, which means that we simulated all the different systems from the different demo sites. So as you can imagine, it was the 4 technology packages. For the one of each is installed in the different houses. And we had a great performance as feedback. So we have ranges of 30 to 70% energy savings, but up to 84% cost saving. Of course, this is not for all demo sites, but the best performing demo site shows 84% cost saving, and the self-consumption ratio of 95% is the best case scenario. Of course, the energy flows that we measured here are only related to heating and cooling to the heating and cooling. So we haven't considered electricity for appliances, for instance. Another great result of the project is happening now, is month 36 of the project, so it's September. When we were expecting to deliver the technologies, well, we have delivered actually the technologies in all the demo sites. One big milestone of the project was also to be able to install the technologies in every demo site. Unfortunately, as you know, COVID had an impact on all the demo sites, on most of the demo sites, and in general on all our lives. So that is not being possible to install in all the demo sites. But the technology have been shipped to the demo sites, and they are all there. Only 3 out of 8 or 9 demo sites have completed the installation by September. Actually, we can say also early October, because we are in the shipping phase now. That's still a brilliant result, I think, for this project, and this thanks to all the partners and the real great consortium I think we have. And then there will be a next big milestone. So what was supposed to happen in month 36 will actually happen in month 43. Our project is 48 months long for now. By month 43, so with only a few more than 6 months time, we will complete the installation in all the demo sites, in the 8 demo sites. And this is brilliant because we have not only, as I said, single family houses, but also tertiary buildings, so very large installation of 200 square meters of solar thermal panels or photovoltaic systems, and they're quite complex systems. So we aim by April 22 to have all the demo sites completed. And we are also in the phase of thinking of an extension of the project, because one of the objectives of the project is also to measure, to assess the performance, for which we have to allocate 12 months. So of course, if we finalize the installation by April 2022 and the project finishes in September, we wouldn't have enough time to measure it, and that's an important part of the project. So we want to have an extension to be able to really assess the real performance of the technology packages. And here a bit about the barriers and challenges, which I agree a lot with Thomas, what he said just before, and all the other presenters, that the budget, and now I start from the challenge number 2, the budget for installation is a very important characteristic that actually in the proposal phase is not always, we are not always able to think carefully. Also, it depends a lot on the different type of partners that we have involved. In the case of Sun Horizon, we have many different type of partners that are the demonstrator leaders. So we may have a municipality, as in the case of San Cugat municipality, but we may also have private consultancy, which are also interacting with the municipalities. On the other hand, we have private owners. So each of them have a different way of behaving, and also this has an impact also on the budget. Besides the permitting, for instance. And going to the barrier number 1, the technologies, they do not always fit the residential owners' requirements. In particular, the residential ones, because in the tertiary buildings, the owners often, well, they don't express themselves, but the users, at least they are not, do not have a voice. So they have energy managers in the large building, and the energy managers are able to take the best decision. But when we deal with residential buildings, the things we have to deal with are different, and a lot more personal, a lot about also the aesthetic. And so this is also a barrier that European projects usually face, the different behavior between tertiary buildings and residential ones, and in the case of Sun Horizon in particular. Another barrier is the COVID-19. As we said, the consequence it has on the construction construction industry. The prices went up. There was a shortage of construction companies for a while, for 6 months, which also delayed somehow our installations, especially in Berlin and Nuremberg. And also the times of execution, of course, because we have to now book the installers in a year time, for instance. And then the challenge number one was a lack of an integrator partner. This is a discussion that we have with the partners every week almost. In this sort of technology packages where we have different technologies coming from different providers, it's really needed to have one main partner which is able to sum them up, to perform the detailed design, the detailed study. And in the project of Sun Horizon, we didn't have this partner. So at the end, we, of course, found a solution, which I think went great after all. But usually, yeah, we commend this. Then an integrator partner would make life easier for all of us. So that's it from my side. Thank you.
Thank you, Federica. And we move to the last presentation of this session, which is the hybrid BOVG project by Salvador Varga. Please.
Good afternoon, everyone. My name is Salvador Varga. I'm coordinator of this hybrid BioVG project. The actual title of the project is very long, so I'm not going to bore you to read it. I think it will be clear what the name stands for as I present the objectives of the work. But before I start, I would like to express my gratitude for the organization to have the workshop in such a nice place. It's been 30 years since I've been to Rome, and it's been a long time, and it gives me a completely different perspective of the city. So thank you very much for that. So the goal of the hybrid BioVG project is simply to convert solar and biomass energy in a single system to provide cooling, space cooling for buildings, space heating, domestic hot water, and eventually, depending on the location where it is applied to, also eventually, for example, pool heating. The goal or the objective of the project is to develop something that is really highly integrated. So this is why the whole system is shown you as a box. The project is coordinated by INEGI. We are a bridge institute, research institute in Porto, Portugal. And we have, besides INEGI, we have 3 academic partners from the University of Graz in Austria, University of Bologna here from Italy, and OST SPF. They changed the name. It's still indicated that HSR, but now we heard the presentation from this university before. And we had in the proposal phase, in the early phase of the project, 3 industrial partners, Hargasner from Austria, Solar Focus also from Austria, and we had a Polish company that actually they are not participants anymore in the project. The duration of the project is 42 months. It was planned for 36, but because of unexpected delays, we extended the project to include the next summer period, so it will end in November 2022. The approach involves the development of design and simulation tools that then can later help the professional people working in the field to design their own hybrid BioVG system. The development of improved performance components, so where we can, it can lead to cost reduction. Also, the development of integration methods. Somebody said before my presentation that the things become more complex. Yes, I think it's a natural course of technology, of things becoming more complex. So we need integration methods, development of control system. It's highly associated to the previous one. And also, this project involves testing and construction of prototypes that will lead the final TRL level to 7. These prototypes, these 3 prototypes are in 3 locations in Europe. A new family home, which was constructed or finished a year ago, more or less, near Porto. We have also some selected offices at Solar Focus Partner in Austria, and also in Switzerland at OST. We have a 3rd prototype that are actually, they are all installed, and partial tests are starting very soon. Okay, the relevant results in 2019, where the project started, we actually were focusing on development of design and simulation tools, identification of required system capacities for the prototypes, so it involved a lot of simulation and modeling. In 2020, we were focusing on the improvement of the performance of the different components and building integration details. You can see here the photographs of a new solar collector that where we managed to reduce initial cost by 14% and improve efficiency. Or you can see in the middle the scheme of a biomass boiler that actually can use multi-fuel for generating heat. And also on the right-hand side, you can see, for example, a chiller that was developed by us. It's based on ejector technology. We heard before that several projects use absorption technology. This is a different approach and definitely more or cheaper solution. On 2021, we were focusing on the development of the control system. Again, I don't have to explain the importance of this part, and all the project partner or the previous project had a different or significant effort in this field. We did as well, and also we have built already our prototypes in the 3 different test sites. The left-hand side, you see a photograph of the Steyr installation. On the right-hand side, you see the near Porto installation. Again, the right-hand side is somebody's house. It's somebody's home. Okay, I did not separate barriers and challenges, and as we talk, as I listened to you talking before, obviously some of the new things came into my mind. Nevertheless, because of the pandemic, obviously we suffered some slowdowns, internal and external. When I mean external, probably you notice the same when you have suppliers. Before we took 6 to 7 weeks to get a component. Maybe now sometimes we get 2 to 3 months. So that's definitely one of the reasons. We also had to slow down because travel restrictions. So we were not able to travel from one partner to the other to solve technical problems. Also was one of the challenges that off-the-shelf components are not available many times for these systems, so you have to develop on your own. That also gives us a considerable amount of challenges, and unfortunately passing away of one of the key partners was a very serious issue in the project that we had to come around and solve it. So this was another challenge in the project. Yeah, and basically that's it.
Can I invite you just for a very short question I have for all of you, which is, I would say, the same question. How long do you expect your solution, so the 3 projects, will take to come to the real market? So do you really think it will take a few years because you are already in an ITRL, or you still need something more to make them real marketable? It's the same question for all the 3 projects.
Okay, so since I was the closest to the microphone, so maybe I will take the first opportunity. Yeah, TRS-7 is definitely, this is what we are expecting by the end of the project. It is definitely closer to the market than any of the previous sessions. And we are hoping that basically after the project, and if we get those objectives that we were aiming at, I would say that in 3 years' time, with some investment, of course, towards a industrial design project, I think there is a good chance that I will see some products on the market with at least some similar symbols that yeah, we have.
Concerning Sun Horizon, the individual elements of the technology packages are already more or less market ready. But for commercializing the technology package themselves, we have to wait for an integrator partners. That's important. It's something that we are now working on in the exploitation task and with the IPR management. So if we are lucky and one of the technology partner decides to lead the entire technology package and so to provide both the heat pump as well as the storage solution as well as the solar component, then I think we are also optimistic and we can go to the market. Thank you.
Once again, from the GeoFit project, but really it's a question for all projects. GeoFit is a combination of 15 or 20 different results. Some are already market ready. Some of the companies are already deploying them in the field. The challenge is how do those 15 results work together for an integrated benefit after a project? And this is a challenge for any project because they don't all get used for all buildings. It would be a magic building where all of those would line up. So how to form those business partnerships to take steps forward so that the retrofitting profession at large can make use of those different results is a wonderful question. And that's why exploitation is a really important work package in any European project.
Thank you all once more. We can now move to the last session, which is the one dealing with the NZEB solutions coupled to renewable heating and cooling. We'll have 5 presentations here. We have more or less half an hour until the end of the workshop, so I would like to ask you, at least to all presenters, to keep the time in order to have at least 5 minutes to discuss before the closure of this workshop. So the first project that is going to be presented is Ensnair by Peru Elguezabal. So Peru, the floor is yours.
Hello, good afternoon. Can you hear me? Yes? Okay. Should I start then?
Peru, we cannot hear you.
No?
Now, yes, please.
Okay. So, good afternoon to everybody. My name is Peru Elguezabal. I'm from Tecnalia. I'm the coordinator of this project, Ensnair. It's the envelope mesh and digital framework for building renovation. So, you can pass to the next, yeah. Okay, so where does the project come from? So basically, we are in a context with in an efficient energy building stock, mainly residential. We are focused mainly on residential, and currently there is a strong promotion on envelope retrofitting, and the general approach, the main approach considered right now is to incorporate insulation. So we do think that these type of activities are an opportunity to incorporate additional technology. So that's where our project, our idea comes from, and it's why don't we do or take that opportunity to incorporate renovation packages consisting of multiple technologies. And also we do have a double page approach or double technology approach. On one side we have and you can see there in the picture, on one side we have the building components, the physical components, what we can call the hardware, and on the other side we have the digital solutions, what we can call the software. So roughly, the project is quite wide, and we have many activities going in parallel with this double approach. But I'm going to focus more on the part on this workshop that deals with renewable heating and cooling. In the end, we do expect to boost the implementation of these renovation packages for nearly zero energy buildings, and that's also linked with the context I mentioned before. We do think that just incorporating insulation is a single measure and quite difficult to meet those ambitious targets of nearly zero energy buildings. So renewables are necessary, and renewables in the whole context, not just incorporating the technology, but also incorporating management and efficient controlling strategies for all those components. So that's again when the digital solutions comes to play. The team is composed by 19 partners. I have to apologize to my colleagues because I had their logos in another presentation, and it's not this one. But anyway, you can go to our webpage, ensner.eu, and you have all the information there. So if you can move forward for the next slide. Okay, the methodology. Yeah, please go ahead. Yeah, okay. So it's mainly a product development activity. So we do expect to develop new products and services and solutions. And as I mentioned, that we have this double approach. We do have to integrate everything into a framework, a supporting framework, what we call. So for the building components, we have what we have mentioned, the modular envelope mesh. That is where we incorporate these subcomponents. And in the other part, in the digital part, it's not there in the picture, but it's where we have this digital platform. A project before, San Horizon, I think it was, mentioned that it's very important, the integrator part. So that's what we expect to cover with this approach. And we do have a couple of partners dealing with this on taking the responsibility on the integrator part. So that's what we have tried to provide with this approach. So for speaking about the technologies that we are about to use and just focusing on renewables, we are going to, we have a strong promotion of solar facades, so incorporating all the technologies, photovoltaics, PVT, and solar thermal. Then we have also smart windows, so dealing with the daylight and so on, and ventilation aspects. And we also do think that heat pumps are matched quite well with solar technologies, as several presenters have already mentioned before. So we also have, it's not in the envelope that it's the main focus of the project, but we do have a link with and based on that overall framework approach, we have a link with a heat pump. So if you pass to the next one. So about the results, the project is on the early stages. We just started this year, so we do not have results yet. I will explain what are the expected results, what we would like to get. So we've been working this year on the definition of the specification, and in the end, it's as I said, a product development process. So we will build during next year our first prototypes, ready to be tested, and we will redesign those and provide a second version of those prototypes, what we call pilot ready prototypes, so that we will be able to install them by 2023 in 3 different buildings around Europe. We have tried to cover quite the geographical coverage of Europe, starting from northern part in Tartu in Estonia. We also have in Italy a demo, and also in Central Europe in Sofia in Bulgaria. So in the end, we plan to install 1,000 square meters of solar panels, and we do expect, yes, I did not include the other years, but obviously we have to then analyze those results and provide relevant inputs. But as it's quite far in the future, I just have focus on the next 2 years. So if you go to the last slide, I think it is, yes, this one, about the barriers, and similarly to the results, we have certain barriers already starting to arise. Personally, I think some others will occur, but we do have started to identify certain difficulties. So one is the lack of confidence of the performance of this integrated solution, and the challenge is to demonstrate that it's worth combining the technologies in the facade. And the other barrier is the different level of knowledge and expertise intervening in the process. In the end, we have people that is expert on photovoltaics, and we have people that is expert on facades, and they don't speak the same language, they don't work in the same way. So it's very important to establish communication channels and to develop this type of platforms and so on. So we do think also that being here, building information modeling, it's a clear opportunity to work collaboratively and under a common framework. So that's in the end our idea. So to sum up, it are those three pictures below. A solar facade is not. It's neither a facade, just a simple facade, and it's neither a simple solar panel. It's a combination of both, and yes, probably when we compare, we also have to take into consideration that we cannot directly compare a solar facade with a facade or a solar panel with a solar facade, because we have to take into account those different considerations, and in the end, yeah, it's a matter of changing the culture and progressing towards this type of solutions. So that was it from my side. Thank you very much. And if you have later on questions, we can comment on those.
We hope we will have time to discuss at the end. We move then to the second presentation of this session, which is by Stefano Avesani from EURAC for the Infinite project. So Stefano, the floor is yours.
Yes, do you hear me?
Yes.
So hi all, thanks for the organization. So I will present you the Infinite project that has been funded under the same call of ENSNER and also Plural. And if you go to next slide, please. So we follow the motto, of course, of renovation of existing buildings, and we have, let's say, invented a kind of renovation 4.0 motto to highlight the need of the industrialization, digitalization in the renovation sector. And if you go to next slide, please. With Infinite, we are 19 partners, and we are working on 3 real demo buildings to be renovated, and we have 6 virtual ones around Europe that will, let's say, be a kind of virtual testing of the methods and technologies we will develop. And next slide, please. So the overall scope is to increase the market penetration and industrialize the all-in-one envelope systems. So the focus is clearly on, let's say, technologies, envelope technology mainly, that has to be industrialized and multifunctional, with the aim to get the buildings, existing building, under overall near zero energy building performance. And I also added this from first to second generation of systems, because we do think there are many experiences, and we have to really build on that. And in the next slide, I have, let's say, summarized the 3 pillars that might really get this renovation 4.0 concept working. So being an industrialized process, a digital one, and with a sound business model. So let's say the 2 most specific objectives are to demonstrate tools like design support tools, technologies, and business model to really boost the adoption in the market of such industrialized approach. And something I like a lot is that this kind of solution for NZEB, so the industrialized one, might have a specific market, let's say. So we have really to understand where and how such approach makes sense. And in the next slide, I will give you an idea a bit more specific of the single objectives, specific ones, which again are about tools, which are fundamental to improve, to ease the management of the retrofit process. And also keeping in mind and really getting a doable life cycle driven design. Then in terms of technologies, we really want to get closer to the market with industrialized envelope technologies, and to rely on attractive businesses. Of course, the yellow lines in the middle of the slide underlines the need to have buildings demand on board, all what is stakeholders from the building demand side, but also from the offer side. So stakeholders and building are keywords in defining the specific objectives of Infinite in terms of keeping into the consideration of the whole value chain, from technology provider to investors to design and so on. And finally, of course, specific objective on demonstration, because we have to build let's say the new market based on hard facts. And these hard facts really comes from demonstration. I go then on the next slide. If you go, please, on the next slide. Yes, I just try to summarize here the expected results. So top left, all what is envelope. There will be envelope kits, robust roof and facades, integrating photovoltaics and solar thermal mainly. And there will be also the integration on the ventilation machine, able to deliver both fresh air and heating and cooling, as let's say heat distribution, and heating, cooling, distribution, and fresh air. And finally, per the technology point of view, we have also the development of a building management system, an adaptable one, really developed based on a stakeholder-centered approach, meaning that has to be really interoperable between different systems, but serving different kind of users. Of course, in operation, energy in operation is an issue for residential buildings, so it's very crucial. In the bottom right, you see the topic of tools. There will be a BIM platform with different kind of plugins to easier and to, let's say, facilitate the stakeholders to approach to the renovation design. In the center of the slide, you see all the topic what is stakeholders engagement needed to, and this is the activity basically that we have done in this first year. So really to consider the whole value chain stakeholders, to listen to them and to, let's say, build with them new technologies. Okay, and then we will have something in the second part of the project, let's say, about more market potential map and EU Observatory on Industrialized Retrofit. If we go on, please, with the slide. Okay, you might know, of course, this graph of nearly of net zero energy building definition. And so we position as an energy concept for buildings ourselves, trying to reducing the demand with the BMS, allowing to implementing optimized control strategies, but of course also with the roof and facade insulating system. And on the other side, we want also to reduce the non-renewable energy supply, thanks to again photovoltaic, solar thermal, and again building management system. This is a bit let's say the energy concept declaration from Infinite partners. And in the last slide, to summarize the challenges. Basically, on the scheme on the right, you might see the keywords that we follow as project drivers, and of which two of them in yellow might sound also very challenging, and I will highlight it now to you. So one is the topic of net zero energy building definition and verification, which is on one side still very discussed and differentiated among Europe states, but also especially the part of being carbon neutral as a direction. So all the topic of life cycle assessment still is a topic to be deepened and more standardized. And finally, second, let's say, challenge or barrier is the stakeholder acceptance. So finally, we can build the best technology ever, the most efficient one, relying on solar sources, and we are doing an Infinite. But if we don't really get stakeholders into the process, they do not accept it either for investment but for the operation phase as well, then probably we are running into failure of the overall approach. That's it, more or less all. So thank you, and yeah, I'm of course available then for the discussion.
Thank you very much. So we can proceed with the third project, which is PowerSkin, presented by Jorge Coworker. Please, Jorge.
Hello, many thanks. Can you hear
Yes.
me? Okay, many thanks, Andre, for having us, and good afternoon to all. My name is Josh Corker. I'm a researcher at IPN in Portugal and the coordinator of the Innovation Action Research Project PowerSkin Plus. We were funded on the 2019 H2020 EEB topic, and we started last 2019, and we are running a full 4-year project timeline. Can you move the slide, please? Okay, basically, PowerSkin, we are aiming to generate prefab stick and unitized modular solutions for facade curtain wall buildings, enhanced with different multifunctional add-on features, combining super insulative elements, solar energy harvesting components, and active and passive thermal energy and electric storage features. So we want to contribute as a project to the speed up of transition of both near zero and positive energy buildings by demonstrating these holistic facade solutions in an operational environment and trying to tread a little bit the path for future exploitation, covering both standard and combined premium solutions, addressing primarily non-residential retrofitting market capabilities. So we are working on off-site prefabricated and easy to install transparent and opaque modules, addressing a wide number of state-of-the-art energy efficient materials, systems, and key enabling technologies, such as, for instance, super insulation elements in the form of low E triple glazed IGUs and vacuum insulated panels, multifunctional nano-enabled coatings for different types of properties such as self-cleaning, anti-reflective, photocatalytic, for instance, the solutions. We are dealing with solar energy harvesting components based on this novel inkjet printed flexible perovskite building integrated PV cells. We are working with thermal storage pattern solutions using a semi-transparent capillarity glass sheets having this microfluidic material for active thermal storage and heat diversion. And obviously we are working also with PCM driven latent heat storage elements in the opaque elements and opaque components. And we are combining all of these state-of-the-art solutions with the integration of an autonomous building electric storage system based on second life e-car lithium-ion batteries connected not only to the PV systems, but also to the grid. So we have a great consortium made out of 6 universities, 3 RTOs, and 5 SMEs. Can you change the slide, please, Andrew? Regarding the main achievements so far, well, in May of this year, we have defined all the materials, the integrated system design, and the performance specifications. This month, we realized the first set of standard opaque and transparent prototype modules, and we just initiated last August the demo buildings baseline assessment. Next March, we intend to finalize the prototype integration of all these add-ons, the PowerSkin add-ons, and continuing their system lab validation. And we expect by the end of August, September of next year to initiate our demo installations and full year demonstration actions in 3 different buildings located in the Czech Republic, here in Portugal, actually in Coimbra, and back in Germany. Then in February 2023, we should have the PowerSkin system lab scale validation completed, and well, before the COVID outbreak, we were aiming to have, by the end of August 2023, the finalization of the performance demonstration in the operational environment in our demo buildings. Let's see if we can fulfill completely this without an extension. but we are aiming towards that goal, along with all the necessary databases and future market entrance guidelines. Can you change the slide, Andre, for me, please? Finally, considering the main barriers for the deployment of these technologies, and I've tried not to list specifically linked to the Power Scheme project, but probably more common to many of the technology developments that we heard so far in very similar project approaches, as we can see, and their pains to reach the market. There are many different types of barriers covering market and technical barriers and other aspects, but I've decided to highlight just a few of them. Obviously, the cost of high-performance solutions, the slow EU retrofit pace, and probably even slower adaptation of disruptive energy-efficient technology solutions. Sometimes the low awareness of a highly conservative construction market that keeps pushing in not providing to reach these technologies close to the market. Different regulatory requirements across different European states. We are still very much dependent on fossil fuel market. We're not embracing properly the renewables. Sometimes, and we already approached this in other presentations, most of the times there are barriers covering the technical complexity of these systems compared with conventional and traditional well-established solutions in the market. And also the highly diverse building and facade types, different uses, different codes, different climate regions, that makes very hard for us to design this universal, I would say universal modular retrofitting solutions. So basically aligned with the barriers, we have some challenges. I have highlighted some of them also. We as important actors should help to build confidence and support market acceptance for these new technologies. Another main challenge is to speed up scale production capacity of many of these technologies, because niche solutions will never reach the market at competitive prices. This smart combination requires the rise of new integration players, and we already heard back in a different presentation from Marina the importance of this integration players to deploy this synergetic engagement of different add-on technologies with different suppliers. And finally, we should work upon reducing modular system complexity and develop what I would like to call low budget and easy to install solutions to assist the retrofit market and achieve the necessary decarbonization goals set for 2050. So that's all for now from my side. Many thanks for your attention. And you can check our website at powerschemeplus.eu. Many thanks.
Jorge, we are a bit short in time now. We need to move to the next one, which is the Plural project, which will be presented by Professor Maria Fonti. So please,
hello.
the floor is yours.
Thank you very much. As you already announced, I will shortly present the concept of the Plural project, which is also one of the three projects that looks at the integration of renewable energy systems into prefabricated facade for retrofitting. If you can go to the next slide, please. So in the frame of the Plural project, we are developing a palette of prefabricated kits that integrate prefabricated facades with renewable energy systems, and that take also into account the building user requirements. And for this reason, we paraphrase plug and play, and we call them plug and use kits. Our approach is, of course, as it can be expected, to select and incorporate the appropriate renewable energy technologies in the prefabricated components that would ensure that we can reach the NZEB status at the buildings that we want to retrofit. We are targeting a variety of residential buildings, and we are hoping to be able to demonstrate the technologies in 3 real demo sites in Greece, Spain, and the Czech Republic, where, as you can see, they cover different climatic zones with emphasis on the cooling demands, and 3 virtual demo sites in Switzerland, Germany, and Sweden, covering more Nordic climatic conditions, where we also expect to demonstrate the capacities of the plural kits. So as I already mentioned, the goal is to optimize these PNU kits for different climates and socioeconomic conditions. The work is undertaken by a team of 18 partners. 60% of them are SMEs and industries that, as you can see, they cover from energy manufacturers to prefabricated solution SMEs, as well as academia and research establishments, and the demo sites as well. Let's go to the next slide, please. So what are we doing? We are implementing our developments in 4 different pillars. The first pillar deals with the design and the manufacturing of these integrated kits. The second pillar deals with the development of appropriate software tools that can combine the design, the manufacturing, and the assessment of these kits in order to support their optimization. The third pillar is, of course, as one would expect, the demonstration pillar for the validation of the developments, and the last pillar is a go-to-market strategy, having identified that this kind of innovative solutions need a lot of effort and a lot of changes in the value chain before they can find a place in the mass production. Let's go to the next one, please. So what have we done until now? We are 1 year old. We started exactly 1 year ago, and the project lasts for 4 years. So in the first year, we defined all the requirements for the developments of our prefabricated integrated solutions. In the next year, we are intending to optimize the performance of our PNU kits that include nature-based materials with PVs and geothermal and also solar thermal solutions. In the third year, we are going to implement the decision support tools and the design software platforms that we are developing, and in the last year will be the validation. So going very fast to the challenges and the barriers, not to spend much time. So the big barrier that we can see at the moment is the market competitiveness. The solutions that we are developing appeal at the moment only to larger residential estates and big contractors. Smaller residential as alternatives, they need to invest a lot. The capex is high, the opex is not yet defined, so the market competitiveness is it's a big barrier for the, as I mentioned before, the mass introduction of this kind of integrated solutions that couple the advantages of nature-based and environmentally friendly insulation with renewable sources, and that can actually lead very easily to NZEB solutions. Another key barrier is the technology compatibility. We have seen in the previous projects that have been presented that all the innovative solutions that are developed and that take into account renewable energy sources are targeting building level renovation or building level interventions. In our approach, where we want to retrofit the facade, we have to have technologies that match the requirements of individual spaces of the building in a dynamic way. And this is a big challenge and a barrier because there are not in the market systems that can cover all the heating and cooling needs of individual spaces in the building. So as a barrier, as a challenge in terms of the market competitiveness barrier, I see the need for development of new business models that take into account possible modifications and new integration of the value chain that would allow the entrance of new players like the prefabricated solution manufacturers that all collaborate very closely with energy system producers that can produce and manufacture an integrated system that can be used for the retrofit. And of course, a very important challenge is to demonstrate that this kind of prefabricated integrated solutions do not set additional barriers in terms of quality, cost, time, and environment in the renovation procedure. And in terms of the technology compatibility, I hope that the development of integrated tools that combine the architectural design, structural design, with the energy system assessment and the manufacturing requirements would help us overcome the technology compatibility barrier. So thank you very much for your attention and the opportunity I had to present our work.
So we come to the next presentation, which will be held by Federica Foligni on the Envision project. So please, Federica.
Okay, thank you very much. So I'm now presenting the Envision project, which is a project focused on energy harvesting by invisible solar integration on building skins. As the name said, the goal here is to harvest as much energy as possible from all the building external surfaces, so what we call the building skins. So not only placing PV on the roofs, but putting them also, for instance, on facades. The approach of Envision is to have technology to exploit to have technologies that are capable of exploiting the near-infrared solar radiation, which constitutes around 50% of the total solar radiation. The consortium is composed by 9 to 10 partners, and you can see here in the next slides the 4 main technologies that the consortium is applying. They are also considered sort of plug-and-play solutions. They are quite high TRL and quite ready for the market, but we, in these 4 solutions that the project presented, actually there were initially 2 solar thermal panels. One was the uncovered solar thermal, and the other one was covered by a glazing, by a glass. In the second one, they were both delivered by consortium partners, but the second one demonstrated to be not feasible finally because of a very high cost, and which didn't compensate the performance, and therefore was discarded. So finally, as a technology package in the project, we only have 1 solar thermal package solution, but we also have 1 PV harvesting glass. So it's like it belongs to the building integrated PV solutions. It's like a windows with a lighter, a slightly darker glass, which integrates the PV performance. And then we have a smart ventilated window, which is a solution capable of producing hot water, and then I will explain how. These 3 solutions have been integrated in the demo sites of the project, among which we have the Dutch residential demo site, which is considered the Nordic demo site of the project, and also the Italian demo site, which is the Savona campus of the University of Genova, where we have installed the first one, the solar collectors, uncovered solar collectors. And then we have the second technology with the PV integrated solution, which is being installed in Pilkington offices. It's been also developed by Pilkington, but it has been installed also in their 2 offices, one in Austria and the other one in the Netherlands. And the last one, the smart ventilated window, has been installed in Savona, always in Genoa, in the University of Genova. So this is a bit of a representation of the system that includes the facade solar thermal panels that has been used and installed in the campus of Savona. So you see that the campus of Savona includes actually a small district, is a micro district with heat pumps and the solar thermal energy storage, and also a mini CHP system. And the solar thermal panels have been connected to this system to generate hot water for the functioning of the network. But also in the campus of Savona, we have installed the smart window. There has been a lot of development going on around this technology, which actually is capable in winter mode to produce hot air for the ambient. It has like a water and glycol circuit, but in winter it provides hot air directly into the ambient, while in summer modes it operates only by warming up the glycol circuit and not providing directly cold air. Actually, this is a mistake in the slide. It only provides warm to the circuits that then in Savona actually goes to the large thermal storage and is not further exploited. The project timeline includes some large time frames, for instance, for the technology demonstrations. What in Envision is technology demonstration actually is a testing of the solutions. So the different technologies have been tested in the Netherlands and in France, and they have been assessed for their performance. In 2020 and 2021, they've also been installed in demo sites. So we have among the demo sites, as we said, the Netherlands social housing, Pilkington offices both in Austria as well as in the Netherlands, and the Savona campus in Liguria region. And then in 2021 and 2022, we will have the in-field monitoring. So once the technologies will be completely installed in the demo case, we can couple them and test their integration in the buildings and districts. Among the barriers that we face in this project, the first one is the pandemic, which caused delays in the Southern European demo site, so the Savona campus, due to the bureaucratic and administrative practices. In fact, the public administration has been heavily affected by the COVID, and therefore we couldn't proceed as expected. But also a second barrier is the building harvesting concept developed for the Nordic demo sites. In fact, here there was some misunderstanding between the partners, which led to further delays and to change finally the demo site. The challenges of the project have been the demonstration and validation of the Envision technologies, which took place at different stages. The different technologies were in fact at different TRL stages, and this made it difficult to actually install them all at the same time. The second challenge is the connection with the housing corporations and the architects, which required always a bit of difficulties in dealing with this integration of technologies in the buildings. So that's all from me. Thank you.
Thank you, Federica. Unfortunately, I have to close now the session because we are already above the time that was allocated for this workshop. So I would like to ask any attendees or even presenters to send a question directly to each NZEB expert that was presenting the project in this last session of the workshop. I would like to thank you all for attending and for the nice discussion. I hope we'll have the chance to promote again the same workshop next year to follow up with our activities. Thank you all, and see you soon, hopefully.
Thank you.